Hello, this is Concrete Bath. Here we have the lecture for that factors affecting compaction of soil. Factors affecting compaction of soil. So if we talk about that standard Proctor test, what was that all about? That was relating that unit weight, dry unit weight of the soil with that water content. So if I know what is the equation for your water content at that gamma dry, do you know the equation for gamma dry? Is that G gamma W by 1 plus E, and at a particular value of that what you call as water content, we can write that value of E equals to Wg by S. Can we write at a particular value of water content, we can write this equation as gamma dry equals to G gamma W divided by 1 plus Wg by S. So I would say your one of the variable in the dry density is that water content. So factors affecting compaction. So first important parameter is there, that's water content. So that's water content, moisture content. After that we say what is the soil type? What is the soil type? So soil type is there, and third one is that the compaction, nature of the compaction. Nature of the compaction. Okay. Nature of the compaction, that is we denote that as compactive effort. Compactive effort. Here we have two different possibilities. One is the kind of that what is the way you are applying that compaction. What is the way of compaction? That is the nature of the compaction, nature of the effort. Okay. Second one is that amount of effort. Amount of effort. We already have talked about that amount of effort. One was in terms of light compaction, one was heavy compaction, standard modified. That is the amount of effort. And second one is their nature of the effort. But that means for a particular kind of soil, we are going either by vibration, we are going to compact the soil either by vibration or by static pressure or by any other method. That we have that n number of methods for your compaction. That is the nature of effort. Okay. And that actually the nature of effort is a function of soil actually. So on a particular kind of soil, your suitable method is taken accordingly from these nature of the efforts. Okay, so let's talk about the water content. Let's talk about the water content. Let's talk about water content. Let's go for your water content. Water content. Okay, your equation for that unit weight, dry unit weight of the soil is G gamma W 1 plus Wg by S. Wg by S. This is your water content, small w. So if I had the plot for different values of W, for different W, so if I vary the W, my gamma is also going to varies. So then we plot that total, and we got a curve that is somewhat in this fashion, somewhat in the form of inverted U shape. Some inverted U shape form of that variation is there with respect to that gamma dry and water content. Okay. Now we want to explain how this is actually happening, how this is actually happening. Okay. So this point is optimum. This is optimum moisture content. At that point we are having some gamma D max. Now we would say that if your water content is just less than, if water content is less, if water content was less, that means at lesser water content, what's happening? Your soil is actually in the stiff condition. Soil is stiff. And if the soil is stiff, so it's not allowing that compaction of this soil would not be easy. Compaction of the soil is not easy. Compaction is not easy. Is not easy. Okay, compaction is not easy. But if water content is more, if water content is more, what's happening? Let's say water content is more for this case. Water content is more. You your the voids that volume of solids are replaced by volume of solids are taken by the volume of water, taken by the water. That means your unit weight also decreases. So if your water content is less than that optimum limit, so if your water content is less than the optimum moisture content, on those values we say that soil is stiff, compaction is not easy. So that's why we are getting less value of gamma D. But on the other side, if our gamma is more, if your water content is more, it is more than optimum moisture content, your after that optimum moisture content, you're because of the extra water that's trying to occupy this volume of the solids. So solids are being replaced by the extra water. Here we can write solids are being replaced. Solids are being replaced by the water. So that's why your gamma also changes, because gamma W less than gamma solids. So that's why here your unit weight also again goes decrease. So we see that for explaining this all of this stuff, we have the explanation that's given by Lambe. So that we write Lambe's explanation for this water content versus gamma. Lambe's explanation. Let's go for that explanation. So actually, how can you compact the soil? If we talk about that clay, how can you compact that? We have talked about flocculated structure of clay. Then once we remolded that, in the remolded state, that was remolded clay was having dispersal structure. We have talked about that. Natural natural clay was in the flocculated structure, but your remolded clay was becoming dispersal structure. So this remolding can be possible. Let's say you are applying that static pressure. Let's say that we are applying static pressure. So if I apply that static pressure on that clay, I want to convert that flocculated structure. I want to convert that flocculated structure in a more uniform more uniform packing, such that volume is less and packing is more, wide ratio is less. In the initial case, wide ratio was more. So I want to convert that flocculated structure into that what you call as dispersal structure, such that your gamma would increase. Let's talk about that now. Let's talk about that. So for let's say that for water content, for water content, less water content. For less water content, that means we are talking about that water content less than optimum moisture content. For less water content, what's happening? Your your flocculated structure is there. Flocculated structure, because of the flocculated structure, what's happening? What's happening? There is, we say, there are strong electrostatic forces of attraction. Strong electrostatic forces of attraction between those particles in that interlocking pattern, because there is interlocking, better interlocking, because of the what you call as electrostatic forces of attraction. They are not coming closer. They are not that is preventing this electrostatic force of attraction is preventing closing the gap. Actually, we are having more gaps here. You can see more number of gaps are there because of this kind of packing. There is interlocking, no doubt about that. But there is more that wide ratio. Wide ratio is more. I want to decrease the wide ratio. I want to decrease the volume of whites, volume of air. So for that, I have to make somehow these particles align in a proper uniform way, such that gamma would increase. So these electrostatic forces of attraction are preventing their closing up. They are closing up. They are closing. Their particle is closing up. So because of this prevention of that, because of the electrostatic forces of attraction, so at water content, at we say that at less water content, what's happening there? At less water content, you are having less gamma. So at less water content, we are having less gamma. Gamma is less. Now we say that one more part is there. I want to convert it into this one. Once it converts into in this fashion, what's happening there? Can you tell me what is the concept there? If you have these particles in this fashion, we would say there is net repulsive forces. Net repulsive forces are there between the particles, and net repulsive forces are there between the particles. And there is already know that absorbed layer, double expansion of that, double expansion layer, that we call it as double diffuser layer also. So that's actually a repulsive agent. So because of the repulsion of those particles, because of the repulsion of the particles, I want to make them more closer now. See the concept here. By the repulsion of the particles, we are making them more closer to each other. In the initial case, there was more electrostatic forces of attraction, but particles were in a non-uniform way, such that your gamma is less and wide ratio is more. But this bond is strong. But the bond is strong. There is net attraction is there at water content less than optimum moisture content. Okay, but at water content that's more than optimum moisture content, your what you call as repulsion is more, but your packing is what you call as packing is better. Packing is better. So gamma is achieved more than when you try to increase the water. So if I write after this statement, if I write when water content is trying to get increased, when you increase the water content up to the optimum moisture content, we say that your uh, that what you call as double layer expansion is complete. Double layer expansion is completes at optimum moisture content. So this is very important here. So when this net, so in the initial case, in the initial case, up to this point, your net forces is that net force is attractive. Net force is attractive up to this point. Net force is attractive up to this point. Then then as we try to apply the force, as we try to apply that static pressure and increase of water, your net repulsive forces are trying to overcome the attractive forces. Repulsive forces are trying to overcome the what you call as attractive forces, and particles try to come closer and closer and closer. But that that net repulsive forces overcome the what you call as net repulsive forces. Because of the net repulsive forces, your double expansion layer, because of this double expansion layer, that is actually because of that adsorbed water of those what you call as water, absorbed water, that's also affecting that. So expansion is complete up to the optimum at the value of optimum moisture content. So at that time your gamma is achieved maximum. Now if I once again try to increase now, if I now increase water content greater than the optimum moisture content, now there is again I would say the volume of solids are now overtaken by volume of solids are being overtaken by volume of solids are being overtaken by what you call as volume of that extra water, volume of extra water, volume of extra water. So that's why gamma again decreases. So the thing here is, firstly, let's finalize that. Let's finalize it. Your water content is less. Let's say that this is our optimum. Your water content is less than OMC. What's there? In that case, your net force is attractive. Net attraction is there. If the net attraction is there, particles are not close. Particles are not close. Particles are not close. There is attraction, but particles are not close because flocculated structure. Because flocculated structure. So they are in a more that haphazard way. So that's E is more. Wide ratio is more. But we say that at optimum moisture content, double layer expansion is complete. Double layer expansion is complete. That means your what you call as your structure that the structures, the particles are aligned in this way now. Particles are aligned in this way now. So more packing is there, more close packing, and more close packing, wide ratio less, so gamma increase. Gamma is max. Now if I again increase the water content, if water content is now greater than OMC, so your DLE is double layer expansion is complete. It was already complete. Now it's not going to increase. It's not increasing now. Not changes. It is not changes. It does not change now. So it's fixed now. So its effect is fixed, but your water is now water takes the place. Water takes place solids. Water takes place the site of solids. So because of that also, your gamma is now going to decrease. Okay. this is the explanation for that curve, why this is the reason for your curve. So that's all about that, what you call as that curve. So from the, we call this side as dry side of optimum, and from the other side we say this is your wet side of optimum. Wet of optimum, we can write wet of optimum. So here we can write the structure here is flocculated, and from the side your structure is dispersed structure. And double layer expansion is complete. Double layer expansion is complete at optimum moisture content. So that's why at that value your of water content, your gamma is maximum at that value, maximum gamma. Okay. So this double layer expansion talks about that. This is related to the that what you call as double layer expansion is related to that repulsive forces. Repulsive forces when particles are placed that in face-to-face condition. Because of that, there is net repulsive forces, and this is very related to it that absorbed layer, and that is all about that double expansion layer. Double expansion layer. So that's why we write here at DLE. So that's all about, that's talking about the repulsive forces actually. Repulsive forces actually. Okay. That was the effect of moisture content with the unit weight of that soil. Okay. Let's say that your gamma dry is actually G gamma W divided by 1 plus W G by S. Okay. Now if I say that my study is all based on your degree of saturation is 1. If I keep that degree of saturation equals to 1. So if I say that degree of saturation is 1, what we get from that? What we get from this equation? Gamma D equals to G gamma W divided by 1 plus WG. So this gamma equation, this one we call this one as that zero, that is 100% saturation, 100% saturation density, 100% saturation unit weight or density we can write. This is corresponding to 100% saturation density. Now, I would say I want that gamma D to be maximum. From this condition, this is the actual equation for your gamma D. I want it to be maximum. I want it to be maximum for given water content. For given water content and given soil, I want it to be maximum. And when that is possible, can you tell me if water content is fixed? So this part is fixed. G of the soil is also fixed. Gamma W is fixed. G is fixed. 1 is fixed. That means only that S should be if the value of S is maximum such that this overall value is minimum, and finally your gamma D is maximum. So I would say for that means saturation, degree of saturation has to be 100% such that volume of air is equals to 0, because air content plus degree of saturation is equals to 1. If your saturation is 1, that means volume of voids is only equals to volume of water. So that means no air is left, no air left in the voids. But actually we saw that that this is not practically possible, that there always remains some amount of, there remains that kind of, we would say, when we try to compact the soil, there is always possibility that at that time we would have some volume of air left. It's not always possible that when we try to compact the soil, that when we try to compact the soil, volume of air is equals to 0. This is not always possible. Let's take that example of field compaction. You are doing compaction in the field, and let's say that road construction is there. So at that time there is not possibility that we are flooding. We are not making the soil submerged. We are not making that sand or soil submerged for your subgrade when you compacted the soil or sand. So at that time your soil is not submerged. That means there is less possibility that volume of air is equals to 0. So there would be definitely some air. So that means your 100% gamma D max is not achieved always. So this means your gamma D max gamma D max corresponding to condition than when saturation is 1. But this means that volume of air should be 0. Volume of air should be 0. So this is not usually achieved, and this is actually a theoretical concept. This is actually a theoretical concept, and so this is corresponding to, we can call it as 100% saturation density for that particular water content. Now, if we have n number of water contents for different water contents, let's say we have n number of water content, W1, W2, W3, W4, W5, and our saturation is 1. That means your equation is a function of water content. It's a function of water content, 1 by 1 plus W. So it's a function of water content such that your line that becomes in this way, that we call it as 100% saturation line. So this we call it as 100% saturation line. 100% saturation line. Okay. Now we have one more equation for your gamma D. Can you remember that? One more equation for your gamma D. Your gamma D is actually a 1 minus Na G gamma W by 1 plus Wg. Your Na is actually percentage air voids. That's volume of air divided by total volume of the soil into 100. Okay. So if I want that, if I say that this total value of gamma D should be maximum, this means that, so if the gamma D I want to be maximum, if I want gamma D to be maximum, that means your 1 minus Na should be maximum. So that means Na should be 0. Na should be 0 such that 1 minus Na is maximum. Your 1 minus Na is maximum only when your Na is 0. So that means your volume of air, that is voids are 0. Air voids are 0. Can we say that air voids are 0? That means volume of air in the voids is 0. That's only possible if volume of water is 100%. So air voids is equals to 0. So this gamma we can call it as 0 air void density. 0 air void density at the particular water content. At a particular water content of W, we are having this density at a value of Na equals to 0. So this density is 0 air void density. And similarly, if I try to substitute the value of Na equals to 0, can you tell me what is the equation we get? So gamma D becomes G gamma W divided by 1 plus Wg. So, but this is actually all. This is same as that of the case when degree of saturation is 1. When the degree of saturation is 1, the value of gamma D is same as that of this case when Na is 0, when the air voids are 0. So G gamma W 1 plus G. So that means they are overlapping. So we can call this one also as 0% or 0% air void line. 0% air void line. 0 air void line. So we can call it as 0 air void line, 0 air void line, or we can call it as 100% saturation line for different values of W. For different values of W, we are getting those values of gamma varying in this fashion. Okay, 0 air void line. Here we can see that the relation here is that is only the function of inverse of that W. So once we try to increase the W, your gamma D goes to decrease. Gamma D decreases because all other parameters are going to remain fixed. So that's the relation we can have. That's why it's decreasing with water content. Decreasing with water content. Okay. 0% air, that means 0%. Okay, right. 0% air void line is equals to 100% saturation line. This is one statement we get. Okay. Now let's say that your value of Na is 10%. Let's say that Na is 10%. That means volume of air by total volume is 10%. Okay. Volume of air is 10%, 0.1 times volume of total soil. And at that time, can you tell me what is the gamma we can get? Gamma dry equation. So that is actually 1 minus, that we can write 1 minus Na, G gamma W, 1 plus Wg. And let's say that your Na, your degree of saturation is 90%. Degree of saturation is 90%. Degree of saturation is 90%. That means volume of water by volume of voids. Volume of water by volume of voids is 90%. So we can write the equation. We know the equation G gamma W. That's G gamma W divided by 1 plus WG by S 0.9. So I would say your 90% saturation line for different values of gamma W, for different values of W, you would get a line for your 90%. So your 90% saturation line, I would say 90% saturation line is not same as that of a 10% void line, air void line. So this is one more statement we get, air void line. And 10% air void line is not same as that of a 90% saturation line. But because we have the relation of S is with air content, not with the percentage air voids. We have the relation with these two. It does not mean that S is 1 minus Na. This is not true. We have the relation for your air content, that is relating volume of voids by volume of water by, yeah, volume of air by volume of voids. But your air content is volume of air by volume of total soil. So that's not the same. So we have this statement that 90% saturation line is not 10% air void line, but your 0% air void line is actually 100% saturation line at that time. So this is one more statement we can get. Okay. So that's all about what you call as that effect of moisture content. Effect of moisture content. We can take a problem. We can take a problem so that we can get some skill out of that compaction. So we can learn some stuff. Okay. Okay. Let's take a problem and we can go with the problem. Let's go. So we have this lab Proctor test. That is the test performed in the lab, and we have performed a few number of trials. And let's say that the weight of soil and the mold is equals to, in the first trial, the weight of the soil plus weight of the mold is 3.526 kgs, and the water content at that same test was 8.33%. And the second test was performed. In that case, your weight of the soil plus weight of the mold is 3.711. Similarly, you can write for the third 3.797, 3.906. And in the fifth one we can have 3.924, 3.882. This is your test number 2, 3, 4, 5, 6. And similarly we can have water content. Water content is also changing. 10.40, 12.33, 12.33, 16.20, 17.92, 20.39. So these are your values related to that test. Now we need to calculate. Now we need to calculate what you call as, yeah, we need to get the optimum moisture content and get the gamma d max. So this can be obtained from the plot of water content versus gamma d, gamma dry. So these two can be obtained from the plot of water content versus gamma dry. So we need to plot all that data in terms of gamma dry and water content. And one more thing we need to have, plot that zero air void contact line, zero air contact line, zero air contact line, and 10% air contact line. So few more data that are given, that G of the soil is 2.68. Your mold is there. Mold weight is actually a 1.89 kgs, and the dimensions of the mold are that we are having height of 12.7 centimeter mold, and diameter of the mold is 10 centimeters. So we need to get the gamma dry. So for that we had to get the bulk density from as per the question, that because there is water content effect, so at a particular value of water content you won't get gamma dry, so you would get some value of gamma bulk. So we need to calculate first what is the bulk unit weight at particular values of W. So for that I would say what is the soil in those all. So I had to subtract the weight of the mold plus soil minus weight of the actual mold. So I would say what is the soil weight of the soil. So what is the weight of the soil? I would say that is 3.526 minus 1.89. So that is coming to be equals to 1.636 kgs. So this is 1.636 kgs. And similarly you can do for all other tests. You can do for all other tests what is the weight of soil. So once we got the weight of soil, now we need to say what is the volume of the mold. That volume of the mold is going to remain fixed. That is going to remain fixed, and that value we can solve separately. That is pi by 4 d square into h. So that's in terms of centimeter cube. So that value we can calculate. That is volume of soil. Volume of mold is 997.45 centimeter cube. 997.45 centimeter cube. Okay, that we also got. Now we would say that what is the bulk unit weight? So solution would be what is the bulk unit weight? Bulk unit weight is actually weight of the soil in that condition, in that particular water content condition, divided by the volume of soil. So here we can write that 1.636 kgs divided by what you have the volume, 997.45. 997.45 centimeter cube. So that would give me some value of gamma bulk equals to, let's say that the gamma bulk is in terms of grams. We are getting in terms of grams. That is 1.64 grams per centimeter cube. Let's say that we got this gamma at that particular value, and for all other data we can calculate. Initially we need to calculate what is the weight here, difference of that total minus weight of mold. So after that we can write the same kind of stuff here. So let's say that the final solution, final values of that gamma bulk equals to 1.64. 1.64 is there. 1.64 is there. 1.826. 1.826. After that 1.913, 2.022, 2.040, and 1.908. These are the values we got. Once we got the value of gamma bulk, we can get the value of gamma dry now. We can get the value of gamma dry now. At that particular water content, we can get the value of gamma dry. So gamma dry would be that 1.64 divided by 1 plus initial water content of 0.0833. Your water content was 8.33, 8.33. So you can write 8.33 by 100. So 1 plus that water content. So that's coming out to be equals to first value, that is 1.515 grams per cc. And similarly for all other values we can calculate 1.654, 1.654, 1.705, 1.740, 1.730, 1.600. So we got the values of that gamma dry. So we need to actually calculate that optimum moisture content and gamma D max. So we can get these two now. Let's try to plot that data. Let's try to plot that data, that is gamma dry versus water content. Gamma dry versus water content. So I would say you had these water content values. Let's say that you had few values. This is 8.33. After that we have 10.40. We have 12.33. We have 16.20, and we have 17.92 as the water content values. And for those we are getting, let's say that we're getting some curve in this way that some points we're getting 1.654, 1.705, 1.740. Let's say that this is your 1.654. After that we have yeah, this was your 1.515. This is your 1.515. After that we have 1.654. After that we have 1.705. After that we have one more thing, that is 1.740. 1.740. After that we are getting 1.730, 1.730. After that we are getting one more, that is 1.660. So we are getting these few values. We are getting these few values. So we have 6 water content actually. One more water content is there, that is 20.39. Let's say that we got these values. Now we need to have a curve that is smooth, that is touching those points, that is going in between those points. Let's say that our general curve is there, a curve that gets formed somewhat in this fashion, somewhat in this fashion. So let's say that this is the curve. When you try to take those actual values with actual scales, so you can get the exact curve. You can get the exact curve. So I would say that peak is developed somewhere here. So this is your gamma D max. This is the gamma D max at some value of gamma, at some value of optimum moisture content. So we need to say what is this optimum moisture content. There's some optimum moisture content we get. So we need to calculate that optimum moisture content, and that can be calculated if I know, if I have that exact uh, drawing of that drawing of those plots after exact position of those points and exact curve drawing. From that we can get the exact values of that gamma d and optimum moisture content. Let's say that your gamma d max is coming to be 1.762, and your optimum moisture content is coming to be 15.2%, somewhere here. Let's say that this is the optimum moisture content, 15.2%, and your gamma d max is, in terms of gram per cc, this is your 1.762. This is actually rho d max. So that is the first part of the problem. Now second part here is that we had to calculate zero air content line, plot the zero air content line. So air content is actually volume of what you call as volume of volume of air by volume of voids, and we have that saturation also volume of water by volume of voids. So if there is some air content, if there is some air content, we have the equation air content plus degree of saturation is equals to 1. So if I want that zero air content line, that means your degree of saturation is 100%. So for the first point, that I have to calculate the value of gamma d at s is equals to 1. So we have the equation. So we have the equation that gamma d is equals to g gamma w divided by 1 plus wg by s. So that's for zero air content. For zero air content. So for a particular value of w and air content to be 0, I can have that gamma d as this function, as a function of that particular equation. So where the s is equals to 1, such that your final equation becomes g gamma w by 1 plus wg. So we can have those values here. So we can say that what is the gamma d max. We can name it as gamma d at 0 air content line. So at 0 we can write gamma d at 0. Let's write gamma d at 0. So let's write that this is your gamma d at 0 air content. That's actually g gamma w 1 plus wg. So we need to substitute those values. We have the g value, that's 2.68. That is 2.68 into gamma w, that is, we can take it as density of water, 1 gram per cc divided by 1 plus water content, that is 0.0833 into g value 2.68, and this value is coming to be equals to, this is coming out to be equals to 2.19. 2.19. And for the other values we can also calculate. For different values of water content we can get now other data also. 2.096, 2.018, 1.1.869, 1.810, 1.733. So it's saying that your values are decreasing with water content. Water content increase, your value of gamma is going to decrease. Gamma d naught decreases with, so here we can write gamma d naught decreases with increase of water content. So we can plot those values. We can plot those values also here. We can plot those values also here. We can plot those values also here. Let's say that we got one of the value as 2.19. So at this value, let's say that this was your water content W1. At this value, we get 2.19. After that, we're getting 2.096. At this location, 2.096. After that, we are getting 2.018. We are getting 1.869. 1.869. After that, 1.810. After that, 1.733. Somewhere here, 1.733. So the curve format here, we can say that's your zero air content line. This is your zero air content line. Also, we can call it as 100% saturation line. 100% saturation line. And one more thing we need to get, that's 10% air content line. So that means if your air content is 10%, so we can say degree of saturation is 90%. Can you say that? Degree of saturation is 90%. Air content is 10%, degree of saturation is 90%. So if I have the equation, if I have this equation now, so I have to substitute the value of S as 0.9. S equals to 0.9. So we can write this one as in this function. So we can write this one as gamma D10 at 10% air content. That's your gamma D10. So we can write the equation gamma D10 now. So we can calculate those values. Gamma D10 equals to G gamma W divided by 1 plus WG by 0.9. So we can substitute for first value. For the first part we can solve G gamma W divided by 1 plus 0.0833 into 2.68 divided by 0.9. So this overall value is going to increase, and that means overall value of gamma is going to decrease with respect to the initial value of gamma d naught. So let's say that this value is overall coming to be 2.1 2.1 2.147 2.147. I think this is 2.147, 2.046, 1.964, 1.808, 1.747, 1.667. So if I try to compare the values with the previous one, at a value of gamma d naught when saturation was 1, you would see that these values are actually initial values are more. Initial value is more with respect to the final value. 2.19 versus 2.147. 2.096 versus 2.046. So the second one is lesser as compared to the initial value. So I would say your values are somewhat little bit lesser as compared to the previous one. Little bit lesser as compared to the previous one. Let's say that at this water content we're getting a value of 2 point how much? 2 point 2.147. 2.147. Let's say 2.147 is somewhere here. 2.147. After that we're getting 2.046. 2.046. Similarly, you are getting these values in this fashion. We can have that in that same manner. That this curve would be always below that point, below those points, below those top points. It would be lesser than those values. Let's say that this is the curve that gets developed finally. This is the curve that gets developed. We can name this one as 10% air content line. Air content line. Okay, that was all about that particular problem. That's your compactions of soil. That's your compaction of soil. Let's say that this was all about that problem. That's compaction of soil. Is there any other thing? Any other stuff that's left? Is there any other stuff left? Let's take that. Let's take one more problem we can have. Let's take that one more. Let's take one more problem. We can study compaction. So your optimum moisture content of the soil was given as 16.5%. gamma D max observed at that optimum moisture content is 1.57 grams per cc. Your G of the solid is 2.65. So we need to get what we need to get. We need to get saturation, degree of saturation. We also need to get percentage of air content at the optimum moisture content. So at this water content, we need to calculate for the degree of saturation. Let's say that we have the equation gamma D max equals to G gamma W by 1 plus E, that's actually WG by S. So for this value of 1.57 equals to 2.65 times 1 divided by 1 plus water content of 0.165 times that 2.65 divided by S. So get the value of S. This is all about that problem. Get the value of S. Saturation 0.635, 63.5%. Second one is their air content, percentage air content. So we have the equation that air content is actually 1 minus 0.635. So that's actually how much? 36.5%, because we need to calculate percentage. For the percentage, we have to multiply 100. So that's 36.5%. Okay. Let's go for second part of the problem. Second part of the problem. Second part of the problem is that get the value of gamma D max, but that should be theoretical. That should be theoretical. Theoretical. It's all about that that optimum, that value of zero air content. That means air volume of air should be zero. That's why we write it as theoretical. At that value, we always get the maximum value of gamma D. So for the gamma D to be maximum, gamma D to be maximum, your equation is G gamma W by 1 plus WG by S. For this to be maximum, your value of S should be 1. Your value of S should be 1. So that's the problem saying that for gamma D to be maximum, and that's actually theoretical. That is actually theoretical. So your degree of saturation is 1 at that time. So let's substitute the values at particular moisture content, where your value of W is at that moisture content. So once we got the value of moisture content, we saw that if I had the curve of gamma D versus W, we got the curve in this way, such that this is your optimum moisture content. At that time, your value of gamma D is actually gamma D max, but it was at a particular value of, this was at given water content, at given saturation, degree of saturation. But if I try to keep that degree of saturation equals to 1 now, if I say I want that degree of saturation to be 1, and now check at optimum moisture content, what is the value of gamma D? Check at optimum moisture content. So at that time, gamma D becomes gamma D max, but this is theoretical. This is theoretical. Let's say the value somewhere here, gamma D theoretical. Gamma D max theoretical. So this part we need to calculate now. About the same point, such that water content is same as that of optimum moisture content. So that's your gamma D max theoretical. So let's substitute the values. 2.6, 2.6, what was the G? 2.65, 2.65 into 1 divided by 1 plus WG. Your value of W is actually optimum moisture content. Okay, this is your gamma D max. What is the value? 1.844 grams per cc. So if I try to compare with the initial value given 1.844. So here we have gamma D max 1.57 only, but at the value of S is equals to 1, your value comes out to be gamma D 1.844 more as compared to the value 1.57. So at this time, so here we have degree of saturation equals to 100%. But in the initial case, that was 63.5%. Okay, let's take one more. Let's take one more. Let's say that your gamma D max by the test of light compaction test, by light compaction test equals to 1.78 gram per cc at an optimum moisture content 15%. 15%. Now we need to get percentage of air voids, and degree of saturation for your G of solid is 2.67. And we need to get the two data, percentage air voids, that's actually Na, and we need to get degree of saturation. If I have the equation for your Na, which of the equations of gamma dry relates that Na? So I would say your gamma dry equals to 1 minus Na G gamma W 1 plus Wg. That's 1.78. Gamma D is maximum at that time. Let's say this is 1.78. And this is 1 minus NA. We need to calculate percentage air voids. So we substitute all of the data, G gamma W by 1 plus WG. So get the value of percentage air voids. Percentage air voids is 6.6%. So in terms of percentage, we are calculating that 6.6%. And for the calculations of that degree of saturation, we have one more equation relating gamma D max with the degree of saturation. G gamma W 1 G gamma W by 1 plus WG by S. So let's substitute the value of gamma D max as 1.78. 2.67 into 1 divided by 1 plus 0.15 times 2.67 divided by S. Get the value of S is equals to 0.801. So if I want third part also, we can, if I try to get the third part also, get gamma D max theoretical. That at that time I have to say either my percentage air voids are equals to 0% or your degree of saturation is equals to 1. So we can write your equation becomes G gamma W1 plus WG. So at that time you can have the maximum value of that gamma D equals to this much. This is coming out to be 1.91 gram per cc. 1.91 gram per cc. Okay, let's go for one more. We need to calculate for the sand, we need to calculate relative density. Relative density of the sand. So this we need to calculate. Okay. And we have the data that natural water content of the soil, sandy soil, that is 7%. Gamma bulk in the field, natural condition. Gamma bulk in the field is 1.61 gram per cc. Now, if we have that Proctor test in the lab, so your mold was having volume of, yeah, there was a mold. So we are performing the Proctor test. Okay, we are performing the Proctor test. So we want to get a relative density for your sand, and for that I have the equation that relative density can be equals to E max minus E natural divided by E max minus E minimum. That's your relative density. So natural condition, from the natural condition data given, so I can get the E natural. Okay, for getting the E max, that means void ratio should be maximum. That means the soil should be in the loose condition, such that your gamma at that time gamma D should be loose. So I had to perform that Proctor test such that my gamma D is loose. So that test is given to you. That test is performed, and the data related to that. Let's say we are having that mold. There is mold. Weight of the mold is given 2100 grams, and one more data is given: weight of the mold plus weight of soil. But the soil is in loose condition, loosest state. Soil is in loosest state. At that time, your total weight is actually 3363.6 grams. And say if I say that one more condition was that weight of the mold was given to you, and one more data was given, that weight of mold plus weight of soil in the densest condition. That was given 3857.4 grams. So I can say that if your total weight is actually more, that means it's saying that it is in the densest condition. At that time, your void ratio would be minimum, and at this time, your soil is low, so void ratio would be maximum. So from these, we need to calculate first what is the gamma dry at that condition and gamma D minimum, gamma D maximum. From that, get the values of void ratios, and finally substitute in this equation. Okay. So we need to see whether it is the Proctor test was performed at a water content 0 or it was performed at some water content. Based on that, we can get the gamma dry. We can get the finally gamma dry. And it's mentioned that these tests were performed at water content equals to 11%. So for both the tests, we are performing that tests at a water content of 11%. So that means we can get now, I would say we can get from the data, we can get first bulk density. After that, we can calculate dry density. Let's solve that gamma d max. Let's solve for the gamma d max. Let's solve for the value of gamma d max. So actually the procedure here is first one that we need to solve for the value of E max. We need to solve for the value of E max. At that time, your value of gamma d should be minimum, and this can be solved from gamma bulk minimum divided by 1 plus water content at that time. So let's go for the bulk gamma bulk at that time. What's the gamma bulk at that time? So gamma bulk minimum is actually weight of the soil, that is minimum weight of the soil divided by volume of soil and divided by 1 plus water content. So we need to say what is the minimum weight of soil. What is the minimum weight of soil? That is actually difference of that 3363.6 grams minus your weight of the mold 2100 grams and divided by the volume of the soil. What is the volume of the soil? So for that we need to say what is the volume of the mold. What is the volume of the mold? So, but based on the test that it is a Proctor test, we have the specifications already known to us, that the dimensions it was having that 1/30th of that cubic feet, or this is also equals to 944 centimeter cube. Is that 944 centimeter cube? And this one we can simplify it in this way, that your 1/30 is there, and cubic feet is actually feet cube, and 1 feet is actually having 12 inches. 1 feet is actually having 12 inches, 12 inch cube, and 1 inch is actually how much, what you call as centimeters. So 1 inch is actually 2.54 centimeters, and that we say that 2.54 centimeters per 1 inch. So we can have the cube of that, and this is actually feet cube, and you divide by that 30, so you can get also 944 centimeter cube. Okay, that's your 944 centimeter cube. So we can substitute that 944 centimeter cube. 944 centimeter cube. After that, divide by 1 plus water content of 0.11. So from that we can get the gamma d minimum. So your gamma d minimum we got. So this gamma d minimum can be equated now with the equation G gamma W by 1 plus E maximum. Because at the minimum value of gamma d, the Lewis condition, at that time your void ratio is maximum. So we need to get now, we have to substitute the value of G. We have to substitute the value of G. Is the G given? Is the G given to you? Is the G given to us? Yeah, G is not given. So here I would say G is not given to us. If the value of G is not given, how can you now solve it? How can you solve the problem now? How can you get the Emax now? If G is not given, you cannot proceed further. You cannot proceed further. This is the value we got, that is gamma D max. Gamma D actually minimum. Gamma D minimum. So we got the value of gamma D minimum, but we don't know how to get the Emax. So what should we do now? What should we do now? So we need to convert that relative density in terms of dry density, in terms of that relative density as a function of void ratio. We need to convert that relative density as a function of dry unit weight. We have one more equation for that. We had derived that in one of the lectures, we know. So that your gamma dry, that your relative density is actually gamma d max by gamma dry natural into gamma dry natural minus gamma dry minimum divided by gamma dry max minus gamma dry minimum. So this is the equation we have. So that means we don't have to calculate for the void ratio. We can directly substitute this value. Let's say that this value gamma d minimum is coming to be equals to, that is 1.206. That is 1.206. We got one of the value as 1.206. Let's say that we got one of the value as 1.206. Now we need to say what is the gamma dry maximum. Gamma dry maximum. Can you now solve for the gamma dry maximum? So I would say your E minimum would be at the value of now. We can write in the same way, for the calculation of E minimum, your equation is that you should calculate gamma dry maximum. At that time, that is actually gamma bulk maximum divided by 1 plus water content, and that's actually weight of the soil. That is the maximum weight of soil we can have in that particular volume of the mold divided by 1 plus water content. So what is the weight of the soil at that time? That's actually that 3857.4 minus 2100. So we can write that 3857.4 grams minus 2100 grams divided by volume of the mold that was given to you 944 centimeter cube, 944 centimeter cube divided by 1 plus water content. So that we can solve that this is equals to, this is coming out to be equals to how much? 1.677. So this is the value we also got, 1.677. So this is your 1.677 and this is also 1.677. Now we need to solve for the gamma dry natural. For that your data was given initially in the initial statement, gamma dry natural. So this is your density in the natural condition that you're having water content of 7% and gamma bulk of the field condition is that 1.61. So we can get gamma dry natural is equals to 1.61 by 1 plus 7%. So this is your value that is coming out to be gamma dry natural, that is 1.505. Now get the value of relative density, 70.74%. Okay. That's all about that chapter. That particular lecture is all about that. Thank you.